Hello everyone, I welcome you to LithuaniaPy. It's nice to be here. I'd like to start off by thanking Viktoras and Aidis for organizing and hosting this event, because I'd really love to see the Python community grow in Lithuania. So I hope you find today's topics, useful and the whole experience fun. So a bit about me from the start. I've come across Python in high school, so now that's more than 10 years ago. Coming from Free Pascal and C++ in school, the flexibility and freedoms of Python instantly kind of captivated me. And since then, it was my go-to choice. So currently, speaking about professional experience, I have around 3 years because I was not always in the IT field. I teach Python on the weekends in Software Development Academy, and I'm a senior Python developer at PVCase in Cone. So, about today, I'll be speaking about web application deployment in the cloud. We'll take a Flask application and using Zappa command line tool, deploy it to Amazon Web Services on AWS Lambda and API Gateway, while discussing the pros and cons of serverless along the way. So let's get to it. Python in the clouds. When speaking about web development, in the early days, you didn't have much options for deploying your websites that you code in Python on, let's say, shared hosting, because the usual shared hosting services would only offer basically the LAMP stack, Linux, Apache, MySQL, PHP, and you would rarely come up on a shared hosting that would offer a mode WSGI, which allowed you to kind of host Python websites. And through the years, that has changed as services developed, let's say, software as a service, and before that, containerization, where you can put your applications in a container, be it Docker, Heroku, and you can deploy your applications as a container. So that basically unlocked your hands to use any technology you want. And currently, at least I have mostly experience with AWS, and it has really nice integration with Python itself. You could actually, if you're using AWS Lambda for simple functions that, let's say, don't have to do with web applications, but have to do with file processing or event-driven software, you can just code them in the web browser and deploy them straight away. So what does serverless mean in this context of web applications? Most of the time, it's a pay-per-use billing model. So that means you don't have a running server 24/7. You don't need to pay for that, but you do have to pay when your service gets used. So in the context of web applications, as soon as you have a visitor, the application serves a request. He does additional, let's say, requests to get static files and everything, and you get billed accordingly for the services that you use. It also offers out-of-the-box scaling. So we'll see when I'll show you AWS Lambda. AVS has regions. So I'm going to demonstrate on EU West 1, which is Ireland region. By default, it has a limit of 1,000 concurrent Lambda functions at a single time. You can always request Amazon for additional resources, but that's the default you get. So when running an application on AWS Lambda and someone visits your website, basically if concurrent calls are made and your Lambda hasn't finished working on a request it previously received, but received another request, AWS will scale the amount of Lambda functions and distribute the work accordingly. So you get scaling without actually managing any infrastructure. And That's very cost effective for websites that have a volatile load pattern. Let's say you have peak time loads at some hour, and previously you would have to kind of scale your servers to handle peak time. And when you don't have the peak time, they would just sit idle. So that's not very effective from a cost perspective. And as I mentioned, it's minimal maintenance and supervision. So the tools are very mature and it's quite easy to use them, as you'll see. So about AWS Lambda, if we're talking about price, the requests cost 20 cents USD per 1 million requests of the Lambda function. So you can expect that's quite cheap. Now, additional cost is duration, 4 gigabyte seconds, and how you understand that is you allocate RAM memory to it. You can allocate from 128 megabytes to 3000. And depending on the time your function works, it will count the time and the gigabytes used, and that will transform into gigabyte seconds, and you'll be paying for it accordingly. The time is rounded up to the nearest 100 milliseconds. So if your function, let's say, is very quick to complete the request, like 6 milliseconds, 10 milliseconds, you'll still get billed for 100 milliseconds. But that's not an issue because when you have these calls, you know, as soon as the call is over and you have like 5 minutes idle time, you've already made up for it if you, let's say, had a dedicated instance running. So one thing to note, compute power is also allocated proportionally to the memory, although the allocation isn't of a linear fashion. And what you discover is if you go above 1.5 gigabytes of RAM, you would start to have 2 processors allocated on the Lambda function. And you should be aware of that if you were deploying an application that only utilizes 1 processor. Most of the time, you don't have to go that high, and it's always about finding the sweet spot. Let's say you want to stay beneath 100 milliseconds, so you would get billed for the 100 and not overpay for the gigabyte seconds. You can also configure a timeout on the function. Let's say if you have some calls that might hang or something, you can protect yourself for being overbilled by telling that this Lambda function should take more than 1 second or 15 minutes. 15 minutes is the max a single Lambda function could run. So if you wanted to go beyond, but that doesn't go for web applications, you would have to chain them. About language support, it currently supports Python, .NET, Go, Java, Ruby, Node.js, and it actually implemented custom support where you can provide bootstrap scripts now. So basically, if you want to test any other language like Rust or something, you know, exotic, you might go for that. Just make your bootstrap scripts and upload them to the Lambda function. So is serverless actually that cheap? You know, 20 cents per 1 million requests? And that's not completely the case because it depends on what you're using. You'll have to use additional services for some functionality. So let's say if I want a Lambda function that takes HTTP requests, I'll have to expose it through a URL. And to do that, I have to use AWS Gateway, API Gateway. That has a cost basically of $1.11 in the Ireland region for 1 million requests, plus extra if you enable caching of requests. So next, if you want to attach a custom domain, you'll have to pay 50 cents per month for the domain. It's called the hosted zone, where you add the domain records, and an additional 40 cents per 1 million requests. And also, as you'll be attaching to that domain, you'll have to create a custom domain name in AWS API Gateway, which will create a CloudFront distribution. And that costs $1.20 per 1 million users. So if you add them up, it's around $3 something per 1 million calls. And you also have to think about your static files, let's say, because as soon as someone visits your website, you know, they might actually make another 10 calls to get your CSS files, JavaScript files, and everything, although that will be cached and subsequent requests won't download them, right? Of course, there's also the database. So if you want to go for basically serverless type of database, you would probably lean towards DynamoDB on-demand mode. On-demand mode also means that it manages the scalability by itself. You just pay for the reads and writes that occur on the database. So if no reads and writes occur, you don't pay anything, just basically for the storage of the database. The gigabytes cost cents. So, as you can see, reads are around 30 cents per 1 million requests, and writes are $1.40. So now talking about the framework, there are multiple tools to work with AWS Lambda and deploy Python applications. One is, let's say, AWS SAM, which is serverless model, something, but it uses its own language syntax and setup, and I didn't find it that much convenient. The other would be Chalice, which is also managed by and developed by AWS team. It looks a bit like Flask, but basically what I don't like about it is that you get vendor locked. If you have a Flask application, you have a Flask application, and you can basically deploy it any way you want. But if you use Chalice, it's already leaning everything towards AWS services. So if you want to migrate to another cloud provider, you'd have to rewrite it, basically. And Zappa is a tool written in Python and manages the deployment to AWS Lambda, and might be just as easy as going inside your Flask application, activating your virtual environment, installing Zappa framework, telling to initialize, you get to pick some selections, and then Zappa deploy. And your function will be deployed on AWS. And I'll show later how to attach, let's say, a custom domain name. Now, for Flask, most of you, if you've been done at least some tinkering with web development in Python, you should have already encountered the Flask micro framework. It's very nice when you want to start fresh and don't really know what you're going to use. So it's extendable by installing plugins. But in the start, if you don't need something, you just don't have it, right? And as you see, a simple hello world application, which serves the text hello world on your base directory on the URL, is just 5 lines of code. And then you would just tell it in the terminal so that your entry file is hello Python, and tell it Flask run. Now, the templating language, in Flask, by default, you get Jinja 2 language. Templating languages are for processing HTML text with special syntax so that it would generate dynamic HTML, inserting the values that you specify in your file. So it has a context. You send it values that this is my value, and inside the HTML file, you write the code to actually use those values and generate, let's say, paragraphs, objects, a list in the table, listing elements. And why I choose, most of the time I use Mako, because it has more freedom than the alternative Jinja or, let's say, Django templating language. You can use any Python syntax that is valid and access system functions. Basically, you're not limited, whereas Jinja kind of limits what you can use from Python inside the templates. And in Django, you'd have to write special functions to expose them in the template. And you can see in the example, all you need to do is import template class from macro template. When it's integrated into Flask, it's even a bit different. You install Flask macro and kind of inject it into the application. But the basic idea is this: you have a string, you say, I'll have a data variable inserted into this place, and then when you call render, you pass it that date will be equals to world. That way you render the text with inserting the value you pass to. And you can see you can use if statements, loops, everything. And now I think it's time I get to coding. So I'll finish here. Let's see. I have a small application for the start. This is the basic hello world, and you can see that if I start it, all I have is this, right? So once you have a Flask application like this, remember what you need to do. You'd say pip install Zappa, and I think I already have it. Yes, it's already satisfied. So I do Zappa init. It says which environment do you want to name it. A bucket on S3 will create for you for storing the files. It's going to basically package where it finds your application entry point. So this is the app. That's why it says app. Then this is an interesting one because it asks you if you would like to deploy this application globally. And as I said, AWS has kind of defaults per region. So I'll be working in Ireland region, but you can deploy your application through the whole world. And you can imagine it will be have a really good latency because according to where the customer is that's calling the website, it will call the endpoint closest to that location. So currently, no. And I see it generated a Zappa settings file. So I say everything's fine. And I tell it Zappa deploy dev. Before this, you would have to set up your AWS CLI and configure an API key. As I have already done that, you don't really see it in the step, and as a default, it goes to my AWS folder and searches for default profile credentials. Thus, it's already connected to my AWS account, and it deployed the function. So now I have a publicly accessible link, which has my function there. So if I change anything here, maybe I'll want to actually render some HTML. I'll create a directory. It's called templates. That's the default directory you want to have your templates in, and that's the one that Flask looks for by default. I'll say HTML file and index. Call it index. Title LithuaniaPy. Let's say H1. LithuaniaPy. Now I go back to my application. What I would do is I would get render templates. Render template. I would go, instead of saying hello world, I would give it render template, say index HTML. Oops, HTML. We can track locally. You check if it's working. Okay, it is. And then what you do is you just go Zappa update dev. Now, this seems easy, right? Because that's the application is quite small, and in real applications you'll have more dependencies, more packages, and everything, and you might run into some various, issues because sometimes the Lambda functions don't accept the packages as is, and then you would have to go to AWS, launch an instance with the Amazon Lambda image, compile your compile your package there on that image so it would be compatible with Lambda functions, and then push it into the file. So there are some things you have to do. And I should also mention that the compressed file, which is being loaded into the Lambda function, is currently limited to 15 megabytes. But if it goes beyond that, Zappa supports lean deployment. That means it zips your application, it uploads it to S3 storage, and then once the Lambda function launches, it has a temporary storage of 500 megabytes it can access. So what you do is you download the application from your S3 folder to the temp storage and import it from there. So it goes into memory. Then it runs as it would. And another thing to mention that these Lambda functions, although they execute for less than, let's say, 100 milliseconds, they still keep running. And we could actually see that if I created a global variable inside, and this we'll use later on. I'll show you how to deploy a Flask admin instance. Again, serverless. Okay, so what I want to show you is how it actually survives after it finishes the call. State, let's call it keep state. I'll just keep it a string. And I'll say that I want a new endpoint, which takes in a name. And I'll say name here. I'll say global keep state equals name, and pass it index. I want to actually pass it like this. Oh, I could actually show you macro templates as well. So to do that, I would install Flask. So if I want to enable that, I do from Flask macro import macro templates. Then I do macro templates, takes in the app, injects all it needs into it, and I use a render template from this one. Then what I would do is I would call, let's say I do this state HTML, and I would say welcome to LithuaniaPy. Let's get a paragraph element and say we have a previous state, and current state. Okay, so like that, I would go here, say state. I want to take the previous state, I'll get previous equals state, previous, then current state will be name, and we can test it out locally. All right, I didn't change the name of the function, so this is state page. Okay, I'll launch it again. Go here, I say columns, previous state is columns, and if I say blah, it goes like this. And if I do it again, it should go Litva, right? Okay, so that works. And if I deploy it to our function, go like this. Now the question is, will I be able when it has the dev inside the name? Yes, it is. Yeah. So what you can use this for is actually for local caching inside the Lambda function. If you want to cache some response, let's say for 5 minutes or so, you could actually make a dictionary where you cache results you got from the database and only refresh them if they expire. That way you implement kind of local caching without using any other AWS options you have to pay for. So this is that, and probably a website like that is not that impressive. So I'm going to quit this one and go to, this is a Flask admin application. Basically, I downloaded it from GitHub. Let's see. If I go here, PyCharm projects. This was the Flask admin master. So if we launch it, it looks like this. Now login, you have admin, and you have this awesome dashboard. Okay, so same goes here, right? I think I have stuff already. Yeah, def, that's fine, fine. Good to go. So deploy def. Oh, I've already deployed it. Okay, so what did, let me get the link, sorry. What did the, oh, actually, I'll show you where it's, where's the source of it. If you go to CloudFormation, what Zappa does, it creates CloudFormation templates. So it gets deployed here. And let me see, updates. Just waiting. You can see this one waits in at 25 megabytes because it has the static files with it. You would optimally use, oh, and I got an exception, valid parameter. And did I type something in while I was clicking around? Type, REST API. Oh, it actually doesn't. Okay. So on the spy, let's call it 2 and see if it goes well. It seems like the templates are off a bit. So we'll just create a new one. Yeah, so what you want to do most of the time is move your static files to S3 service, and you can create, tell it that this bucket will be a website. So you don't have to handle and serve static files from Python Flask. That's what you usually want. There you go, deploying to API gateway. There we have it. And you can see it's here. There we go. And now you can see that it tried to do the admin when it actually has the dev inside it. So it broke it. You would have to go around these issues by setting different, let's say, you could pass the URLs from an environment variable, which you can set in AWS Lambda, but now we're going to resolve it by just attaching it to a real domain name. So I'll go into API gateway. Let's see the APIs I have. LithuaniaPy def. I have a custom domain name ready, called LithuaniaPy, and I'll tell it to map to this application dev environment. So now, if I go to right, did I set up? Right. What I forgot is Route 53. Route 53, API gateway is this one. I'll actually copy the name. Yeah, this is the dashboard. Yep. And to allow it to access, I have to tell it just LithuaniaPy. It will be an alias of CloudFront distribution. This from API Gateway. I create the record in the DNS records, and let's see how fast it will refresh it. By the way, we'll soon have a load test for it. I'll show you a bit. Let's see. Spawn more workers. I have a compute instance set up on AWS, which has 16 cores, and I'll launch requests against the function. But Lithuania, did I get the URL incorrectly, or did I not save the mapping? Dev path9. Let me check. This is the demo gods. Always when you do a demonstration, something must go wrong. Is this the one? Or yeah, this is the admin one. Okay, Lithuania. Oh, I'll save before I can from the get-go. Domain names. Lithuania. Distribution is fine. So wait, is it a regional? Oh no, edge optimized. Okay. Dev path should be good. So well, sorry. I hope I didn't make just a typo, but no, doesn't want to.
No, everything's all right, you know.
Yeah, okay.
Sometimes that happens. Nobody's safe from that.
Yeah, the interesting thing is I tested this today to make sure it works, but I see that it didn't go still as planned. Okay,
you know,
so
it's Murphy's Law. You can't do anything about it.
Okay, so what we'll do is we'll just go and fire at the serverless dev function. This is the simple one, so it has least overhead, let's say, and you can see this is the one that tells welcome LithuaniaPy. So I give it this link, and as I said, I have locus deployed, and I'm going to go with a link. Let's say 10,000 user simulation. What this does is it simulates a user visiting randomly between 1 and 3 seconds. So they should equal out to 3,000 requests per second. And the hatch rate is 100 users at a time. So,
sorry to interrupt you, Edvardas.
yes.
There are some people suggesting some options. What could have might went wrong.
Let me see.
Yeah, you can just click on the chat and you'll be able to see, you know, what people texted, or if you want, I can read it out loud.
Yeah,
so
you can try.
Yeah, so the first suggestion came from Edvinas. He says that alias had comma at the end. Don't know if it's supposed to be there. And another suggestion is from Matas, maybe HTTP instead of HTTPS.
HTTP where? Here you don't even specify, you just specify the distribution, and as it kind of is an auto select, that dot, oh, maybe it's not, maybe let's see. Yeah, maybe I added a dot there, actually. Good catch, if that works. And, no, not yet. If you want to try HTTP, as it has an SSL certificate attached, automatically redirects it. But it might be something wrong with API gateway. Okay. No, so I'm not really sure at the moment.
That is totally okay. I mean, you know, thank you, Edvinas and Matas, for the suggestions. You know, it's okay. Not a big deal.
Yeah, so back to the load testing. Locust is now running on an AWS instance. I'll show you. This is running instance. I've connected to it through SSH. You can see it's hatching users distributedly. And it has 32 CPUs, which are 16 real CPUs because it uses hyperthreading. So once you launch it, it's still running. It's already hashed all the users, and you can see that the requests are coming in at around 5,000 users per second. And the current response time is around 20 milliseconds, 29. So that's the scalability I was talking about. And basically, if you wanted to hit the limits, let's try 30,000, because there's a hard cap on API gateway. If you saw when I clicked on throttling, APIs, doesn't matter. This is Colonus. No, I don't want this one. I want the serverless. This is the simple one. And you can see the rate is 10,000 requests, and it disables the bursts. So it was actually limiting the burst to 5,000. Maybe that was, okay, now it's going up. But you can see that the response time isn't really drastically increasing. So with a few, let's say, lines of code and a few lines for deploying your application, this is the scalability that you basically get for your function. So if you have peak time traffic, you can see that it shouldn't be a problem. And if you need more than 10,000 requests per second, you would just need to request AWS to raise your limits. So I think that will be it for me. Oh, we can see it's rising a bit, but yeah, I'll stop it there.
All right, so Edward, thank you. You know, we all know that we run into some problems each day, and you know, it's totally fine. Don't worry about it. And you know, what I'm happy to see is that you also have some solutions that could potentially fix this. Unfortunately, you know, we have some limited time, and you know, if all of the attendees have any questions, we can go ahead and, you know, you can start asking them right now. We have 15 to 20 minutes for that, and we will move on to the next presentation.
Yeah, I can actually see the chat now once I've disabled the screen share.
Probably due to the screen share, you were not able, you know, to see what were people typing. So okay, so we have the first question, and it says, how do you clear the global cache?
Yes, that is what you have to look out for, because there is no real way. There's no real way to clear the whole cache, because it might appear on a random instance when the website is under high load. So if you're looking for consistency, don't use the cache on the Lambda function. How do you manage Redis and Celery on AWS? Well, you can run Celery on a separate, at least in my previous work space, we used to run it on an EC2 instance, and Redis was hosted from AWS as a prepared solution. So you can launch a Redis instance, just you have to pay for it when you're not doing it yourself. And Celery, Yeah, just EC2 instance, you expose the IP. You can attach the IP to Route 53 to a domain. And that's basically it. Managing, you usually go through, connect to your instance through SSH and do what you need there. What would be the typical continuous deployment pipeline? Well, as you saw, you can have stages. You can name it dev, staging, production environment, and basically from the branches you have to use different settings files, or not forget which stage you're deploying to. But I think you could set it up on AWS code build, just that we didn't really use Python to that extent to deploy it for code deployment. Does it conflict? Well, it is just an abstraction of CloudFormation, which is what Terraform or Ansible, no, Ansible though, you created, no, Terraform I think still uses CloudFormation. But yeah, Zappa is just an abstraction on top of CloudFormation, so the templates would conflict with each other because one would try to override the other, I guess, if you give them the same stack name. So you have to decide on what you use. If Zappa is not enough for some features, you should go on to making your own custom CloudFormation templates. You can use the software development kit, which is kind of the latest abstraction from AWS for that, or just other software like Terraform.
Go ahead.
It's not, that's what you have to decide basically. It depends on your website. If you have, you don't have any peak traffic or anything, which is probably what you will have when you're using a shared hosting for €5 a month, which handles the load. So it all depends on the visits. You would have to test basically if it goes beyond that once you have it deployed on Lambda, or if it's not, because there is some threshold in which it's more convenient for you to start up your dedicated instance and not use AWS Lambda, especially if you have very consistent load, like let's say messages or inputs coming in from Internet of Things or everything, where you know the amount of traffic you have to serve. So yeah, it's always negotiation. So you have to see at which threshold it's better for you to step out of AWS Lambda to a dedicated service. And another note, you can't use async in AWS Lambda. So it's not like it can send you 5 requests to handle in a single Lambda execution. It handles them sequentially. So you can't really use the benefits of current async frameworks of Python.
All right, so I guess we still have a minute or two for more questions. If there are no more questions, then I will say again a big thank you to Edvardas for this great presentation. I have been recording it, so we will see how is the quality of the recording, and we will decide, if we want to upload it or not somewhere. And moving forward, we have our second speaker today. His name is Karolis, and I am going to correct myself. At first, I told the name of the presentation incorrectly, and trust me, it sounds a lot cooler than what I described it. So, without any further ado, we will have Karolis, who will present Hunting Hydra Parallel Python.
Hello, give me a second to share my screen. So here it goes. So today we are going to talk about parallel Python and why it's a Hydra and stuff like that. A quick moment about me. I do some programming stuff with Django at Speronus, and I teach at Kaunas University of Technology, where I work as an associate professor practitioner. So quick outline on what we're going to talk today about. So firstly, I will introduce you to processes and threads and difference between them. Then about threads in Python. Then we will talk about functional programming real quick. Then we will go back to Python thread and talk about thread pools. Then a little bit about multiprocessing and conclusions. So first of all, what is a process? What it basically is an execution of a program or a part of a program with, that has its own memory space. So if we have two separate processes and we have a variable in one of them, the other process cannot access that variable. And all Python scripts are executed by a Python process. So what happens when you start a Python application? Python interpreter starts and then reads the code that you have, and it executes it. So that one instance of a Python interpreter is its own process. In contrary to this, if we have a compiled program like C++ or Rust or something like that, they are run as a process themselves. So the program itself is a process rather than a separate Python process that reads your program and executes it. In contrary to that, a thread is also execution of part of a program, but it shares memory with other threads of the same process. So if we have a process and it launches separate threads, those threads can see the same memory. So that's the main difference between them. And because of that, threads are much more lightweight. So launching a full process is much more costly than launching a simple thread. And a process always consists of at least one thread of execution. And if you code something in Python without specifying that you are going to use any threads, you will use one. So if we run multiple threads or multiple processes at the same time, we may speed up program execution. That's what multiprocessing and multithreading is created for. Basically to speed up your execution by utilizing several CPU cores at once. And current processors allow extreme concurrency levels. That is rising really quickly. I think next year we are going to have even larger numbers. Current Intel i9 processors can run up to 36 threads concurrently, and Threadrippers are insane with 128 threads. But if we only do sequential calculations, we only utilize one CPU thread. So if we have a powerful machine with over 100 of threads, and we utilize only one, so we're wasting some resources. And even the low-end machines nowadays have at least 2 or 4 cores to allow several threads at once. So if you're using only one, most of the time it's some kind of waste of resources. We could achieve our results of our computations faster than just using sequential calculations. So a quick intro into how we create threads in Python. Python has chosen a low-level thread model similar to other languages, like in Java and C# and C++ and Ruby and many others. We have thread class, and a thread object manages a single thread. So it has a constructor, it has some methods, and we can interact or control a thread using those methods. So first of all, about the constructor. The constructor accepts a function that we want to run in parallel. So we have to have a function, a separate function, and if it accepts any arguments or keyword arguments, we pass them as special arguments to thread constructor called args and kw args. If we only create a thread object, nothing happens yet. We have to start it. So we can create many thread objects, but if we don't call start, we will still be running on a single thread. We have to call start. And another important method is join, because if we start our thread, if we don't care when it ends, then it's fine to just leave it started. It will run until completion. If we need some results of the thread, or we have to know if the thread has finished, we have join method. So if we have our main thread and we have created some threads other than the main, and we call join from the main thread, it will block the main thread. So what it means to block? It means that our main thread is sleeping until the other thread that we call join on is woken up. So I will give a quick example. It looks a little bit better on PyCharm. So what we have here, we have a function that we want to run in separate threads. It's called count slowly because it obviously counts slowly, because who wants to count quickly anyway? What it does, it prints its name and its iteration number 5 times with a 200 millisecond interval. And what we want to do is we want to launch 3 of those, so that they, at the same time, they're printing to our console at 200 millisecond intervals. So we have names for our threads. We have 3 threads, thread 1, thread 2, and thread 3. And in order to create the object, I'm using list comprehension here. So what it does for each name in our thread names, it creates a new thread. Target is the function that we want to run in our thread. So in this case, it's count slowly. And since it accepts one argument, we pass args parameter to our thread constructor. It's going to be a different name each time. So here we have 3 thread objects that are created but not yet started. So what we do next is we have to start our threads. So we iterate over the threads list and we start our threads. And we want to wait in the main thread until they are done. So what is going to happen if we launch the program? Here our threads will start printing as written in this function. And our main function will wait for each thread to finish. We just want to join on all threads. So order in which we join is irrelevant in this case. If the thread is already finished and we call join, it will just return instantly. If a thread is still running, it will wait for the thread to finish, and our main thread is going to be sleeping. So if we run this little demo, we see that we had some prints coming not immediately, but in 200 millisecond intervals, and all of those threads are printing their iteration numbers in parallel. Quick note, don't do this because this is low-level stuff. Python has much nicer, much cleaner high-level abstractions over this, and these threads, raw threads, should be only used if those abstractions don't meet what we want to achieve. They don't allow that. So this is just a quick demo on how the low-level stuff works. So if you use those abstractions, something like this is going in the background. And if you're playing with raw threads, a bunch of problems come up. So I would just recommend avoiding using directly this. So getting back to our presentation, those threads could be used to speed up processing of large data sets. And work is divided between the threads so that they could process those parts in parallel. And if we divide our work like this, this is called data parallelism. There's a special term for it. This is what we are going, our main focus of this talk from this point is going to be about how to process those, or either large data sets or maybe smaller data sets, but where each iteration is costly. So in order to delve a little bit deeper, we have to understand some functional programming principles. So those 3 bullet points that you can see on the slide is the very basics of the functional programming. There are variables are never updated, but it would be in Python, of course, we do have variables, but in pure functional languages, we don't have variables. Everything is either a function or a constant. Technically, a constant is also a function that always returns the same value. So we don't even really have variables or constants, but since it's Python, we have variables, but they should never be updated. And we also don't update any external state. So if we have a file or a database that we want to write to, we don't do that in functional programming. If the function is doing something like that, it is not pure. Because a pure function is a function that accepts parameters and returns a value based on those parameters and does nothing else. If it does something like date time now or date today, it's not pure, because if you run it another day, it will return a different value. It has to do absolutely nothing besides getting our parameters, calculating something based on those parameters, and returning the value. Then it's pure. So that's the 3rd bullet point, that external state that depends on time is not queried. So it's either time itself, or if we read from a file, if we read from the file today, somebody can change that file tomorrow, and if you read it tomorrow, it can have different content. So in a sense, it also depends on time. So this should be interpreted as a broad term that does not depend on time. So one of the operations that comes from functional programming is map. We have already seen one map in this demo, in this presentation. Python has a special syntax for it. It's called list comprehension, and it's that on the first code line that is on this slide, we can iterate. We have some kind of list or tuple or any iterable that is called dataset in this, some kind of variable, and we can iterate it, iterate over it, and our goal is to get a new list where each item is calculated from one item from the previous list. So we have a theoretical function that's called function, and what we do is pass each item from the dataset to that function, get some result, and put everything into a new list. Python also has a built-in function that is called map, because it's a map operation. It does just this. The difference between those 2 lines is that if we're using the first one, we get a list immediately. If we use the second one, our result is a generator. So what it means is when we call this function, it does nothing. Basically, it just marks that we have a function called function, we have a data set, a list of some kind, and when we will try to iterate over it, then it will start computing. So this is how Python generators works, and in larger programming language theory, this is called lazy evaluation.
Pythoną darot. Tai jūs ir Karolis abudu Pythoną tvarkot?
Taip.
Kaip čia taip gavosi?
Nu, ką žinau, Karolis nuo pat pradžių su Pythonu kodino, kai įdarbino po pirmo kurso.
O tu iš paskos?
Jo, iš paskos biškai.
Okay, I think we can continue a little bit on this. So, about that map operation, it only works well if our function that we use in map is pure, or the side effects are isolated for each iteration. So what it means for the side effects to be isolated is for example, we have separate files, and each iteration writes to a different file. Then our side effects are isolated. If each iteration writes to the same file, then those side effects are conflicting. So that's the difference, and it's very important when we will start talking about how to make a parallel map. So either our function should be pure or the side effects should not conflict, either of those. Because if we have some side effects, like modifying a variable or writing to the same file or something like that, even technically, even our previous example where we were printing to the console, we were printing to one console from 3 threads. So we are lucky that everything came out on separate lines, but it's just pure luck. If we had many prints, the output would be really messed up. So if we meet those conditions, our functions are pure or all the side effects are isolated, then it's easy to parallelize the map. Because when we launch threads or processes or whatever in parallel, we don't control execution order of those operations. If we have a simple list and we build a list comprehension or just iterate over the list, it's always in some kind of defined order. When you want to use parallel computations, everything happens in parallel. So by definition, there is no defined order because everything is happening at the same time. So it is very important that our function does not, our map does not depend on execution order. And if you meet those conditions, that the functions are pure or side effects are isolated, this condition is always met. So it is very important to structure the code in such a way that we can shuffle the list and nothing changes. It's irrelevant for our application in which order everything is evaluated. Python has a cool abstraction that is called a thread pool. What it does, it is built specifically for dataset mapping using threads. So what it does, it creates a set of threads that is ready to be assigned a task. So we launch some threads, but they do nothing. And then we can call thread pools methods and assign it some work. And it will do it in parallel itself. And all the thread handling is done by Python. So we don't have to create thread objects ourselves. We don't have to call start. We don't have to call join. You don't have to do nothing like that. Everything is handled by Python. And this is exactly what we want. And a quick demo, I will again switch to our code window and switch to another example. So here we have a function that is not yet parallel, but what it does, it pings all the subnet of IPs. It's a local subnet from the last IP part is a number from 1 to 256. And I probably have only 3 or 4 connected devices, maybe 5. So if we try to ping everything, there will be a good timeout. So I will just demonstrate how long it takes with just 5 IPs. So what it does, it will construct a list of IP addresses. Then we will use map operation where we have a function ping URL, which accepts an IP and returns if that IP pings or not. So it's a Boolean. And we will map it over a subnet. So it will take an item, each item from subnet, pass it to ping URL. And we will then filter only those IPs that returned true, status true, so we know they ping, and then we will print everything. So since we use map here, it returns a generator, and this expression here, it is not a list, it is also a generator. Note the different parentheses instead of brackets. So it also returns a generator, so it will print as it pings. So let's run it, and it will take some time. So we have one IP that pings, and it will check some other. So this is something that we want to speed up because that's only 5 IPs. We want to ping the whole subnet of 256 IPs. So I will not bother launching this because it will take several minutes. what we want to do is we want to ping our subnet in parallel. Note that our function, what it does, it calls ping on a specific IP. And if you ping several IPs at the same time, those pings do not conflict. We just send requests and accept responses. So they are not conflicting. So that's a good candidate for parallelization. So if you want to use a thread pool for this, what we do, the best way to do this is using with keyword, because it automatically deallocates our threads, destroys them when this block ends. So we create a thread pool, and we will create a thread pool of 255 threads. I have 8 threads on this machine, but since our threads will wait most of the time, it's fine to have 255, so it will be 1 thread per operation. Please note that there is a thread limit in operating system. It depends on the operating system, but it usually exceeds several thousand threads. So if you want to run like 10,000 threads, it may not be possible. So be careful to not run into this limit. So we create a thread pool, and what else we have to change is, instead of just map, called pool map. So we changed 1.5 lines, and what we basically have is a parallelized version of this. So note that I'm running with 256 IPs, and instead of several minutes, whoops, I pinged the broadcast. Maybe it didn't bring anything, it didn't break anything. So it will take a couple more seconds and we should be done. So we have 4 IPs that ping, and it took roughly the same time that it took us to ping just 4 or 5 IPs in sequential order. So those are the benefits that we would like to achieve using multi-threading. So switching back to the presentation, there is one issue with threads. Python interpreter itself is not thread safe. And as I already mentioned in the presentation, our programs are run using Python interpreter. So if Python interpreter itself is not thread safe, what that means is that it cannot run more than 1 thread at a time. And this is fine for some applications, as we have just seen, specifically for those operations where we have a lot of input-output actions, and we have very little CPU-bound actions. So our ping, what it does, it sends a request and then waits for a response. And since it waits, it does nothing. So that thread is swapped out, sleeping. Another thread can send a request, and we have a significant speed up. But this effectiveness depends on CPU usage of a single task. So if our ping request takes a millisecond or 2, and then we also receive a response, also a millisecond or 2, but we have to wait for like 5 seconds for the timeout to finish. This is not CPU bound, this is input-output bound. The same goes if we're reading from different files, provided that you use some kind of SSD with good random access speeds. Threads are mostly used for this. So Python is basically a Hydra, because it has many heads, many threads, but only one head can act at a time. So it's a weird Hydra. And what we have to do is hunt it. So don't forget to always profile. If you're building code with threads or processes, with parallelism, always profile, because premature optimization is root of all evil. If your speed up benefits are not worth the extra complexity, don't do this. So in our example, everything was pretty simple, but sometimes it gets really messy and it's just not worth it. So always profile. So what can we do if we have CPU intensive tasks? Python has another module which is called multiprocessing. And Since threads are not effective for CPU-intensive task parallelization processes, multiprocessing takes a different approach. What we do instead of launching many threads, we launch many separate Python interpreters. So at the point that we create our processes, it forks. So it creates a clone of a process. So it has all the same variables, all the same memory, just duplicated. And from that point, each process runs on its own. So it has a very similar interface to threads. And if you wanted to use to build our first example where we printed out some iteration numbers and thread names with processes, we could do that. We just would need a different import and a different class, and everything stays the same. And the same goes with our pools. So it's a double-edged sword really, because a process is a full separate Python process, and we cannot have shared memory. Well, except when we can. There are tools for this, but I think this goes beyond the scope of this presentation. But what is most important is those processes may run in parallel, and we can utilize them for CPU-intensive tasks. So the main advantages of this is that separate memory model is easier to reason about. If we know that if we changed something in one process, it has no effect on the other process, it's much easier to reason about each separate process than reasoning about a code where change in one process would change everything in all other processes. So it's just much easier to reason about that code, and it's easier to maintain. And another advantage is that our tasks can run truly in parallel, not just like in one real thread, but truly in parallel. Disadvantages is that creating a process is much more costly than creating a thread, because we have to duplicate the memory. Operating system handles threads and processes differently, so it takes more time for operating system to create a full process. If we need some kind of data exchange between processes, it's more complex and more costly. And shared memory is hard to achieve. And we sometimes do need shared memory. We will see in our example that I'm going to show you that it's really a little bit harder to do that. So here's our example. I will also switch to live code so that we can try it out. And what we have here is a function that is called mean pixel. It is not actually mean in a sense that it tells you bad words, but it's average pixel maybe. And it accepts an image path, which is a string. And it reads that image, it reads all its pixels, and then it iterates over those pixels to calculate the mean of R channel, G channel, and B channel, and returns all those three values. And we have a directory called images. We have several images in there. And we do something similar that we did in our previous example. We call a map on all those images. We pass each image name to our function mean pixel. And what it does is then prints mean pixel for each picture. So if we launch it, it takes roughly 1 second for one image. Since this is also a lazy map, it prints as it calculates. So it's roughly 1 second per image. If we wanted to speed this up, this is more CPU intensive than the previous task, because we have some computations in here, in those lines. This is a little bit more CPU bound, so it makes sense to use processes. So if we want to use processes, we have an import already prepared. We have to import multiprocessing pool instead of thread pool. So everything goes the same way. If we leave empty parentheses, it will create as many processes in our pool as we have computing cores. So that is fine in this case, because I have like 6 images and it will map nicely. So instead of simple map, we do pool map, and we have parallelized our program. And if we want to see our results, it should take a couple of seconds instead of like 5 or 6. So we have achieved a really nice speed up. Basically those process pools look like that, but very different stuff is going beyond the scenes. We have, with creating this pool, we have forked our process probably 8 times because I have 8 threads of computation on this PC. Another thing that I want to point out is we pass image paths. We don't pass pixels themselves to our function, because if we wanted to pass the pixels, processes have shared memory. So if we wanted to pass a list of pixel sets here, what Python would have to do is to copy each of those, then send it to another process, because they have separate memory. It would have to send it. There's a mechanism for that internally, and it takes quite a lot of time, and it really neglects all the speed up that we have in the first place. So when using processing pools, with the processing pools, be sure that your arguments don't take a lot of space. So since this is a list of simple strings, just file paths, then it's good. But if you wanted to read images in main thread and then pass pixel data, it would be much slower, basically same speed as sequential version. And then it would not be worth all the benefit that we gain. So once again, always profile, because you have to check how much overhead process pools creates for you. And if you want to compare multiprocessing and multi-threading, it's like having an army of snakes versus a single hydra that has only one active head. So an army of snakes is much harder to maintain, much harder to create, because you need many snakes. You have to clone them, and a single hydra is much easier, but it has its limitations. So multiprocessing is effective where CPU usage of a single task is closer to 100%, but it's rarely that, because not all the time our processes that we create utilize 100% of processing power, even on a single core. So multiprocessing has many more possibilities. They go a little bit beyond our presentation, but I will just mention them. We can exchange data not only via method parameters to map, but we can also use pipe and queue objects. Pipe is quite literally a pipe with 2 ends. It is used for one-to-one process communication. So if we have 2 processes, and one of them is doing one thing and another one is doing another thing, and they need to send messages to each other, you can do this via pipe. How it works, it's basically when you create a pipe, it has 2 ends, and you pass one end to one process as a parameter and another end to another process, and then they can exchange data. Both of them can write and read from their ends. So this is good for event handling. So if we have some event system and something happens in one process, we want to send a message to another process that handles something. So this is where pipes can be used. Another thing we can use is queues. They can be used concurrently by multiple processes, not just for one-to-one communication. And this is good for consumer-producer tasks. So we have some kind of producer that produces some kind of data, and then we have some consumers that want to consume that data. So they use queue as a place for data exchange, as a buffer, and this way we can achieve producer-consumer on Python. So several conclusions. What I want you to take away from this is using functional principles allows easier parallelization, and I couldn't stress this more. The 2 latest books that I have read on concurrency, one of them has like 1/3 of its content just on this. That's how you can use functional principles parallelize your programs. And another one is about C++, but even that book, C++ is not a very good functional language, but it also stresses that at least you have a functional interface to your functions. If your function is a map, you can try to speed it up with parallelism. If it's I/O bound, you should use multithreading in Python. If your function is CPU bound, you should use multiprocessing, and always profile. So, any questions?
All right. Thank you, Carlos, for this really interesting presentation. And definitely, if anybody has any questions, feel free to send them into the chat. And while we are waiting for the chat, here we go. So great overview. I suspect the tricks of this presentation are unusable in AWS Lambdas of the previous presentation or not?
So I'm not very familiar with the AWS Lambdas, but since Edward has said...
I can answer.
Okay.
Yeah, as I mentioned, if you allocate to a Lambda function more than 1.5 gigabytes of RAM, you get 2 CPUs. So you could use 2 CPUs for some load task. If it's, as it is said, a CPU-bound task, then yeah, you can distribute it. And most of the time, if you're using Lambda and you want to break up something, you use one Lambda to process the input, break it down, and trigger additional Lambda functions with the subset of the data. That's the way you scale on Lambda. And by the way, that URL is up. All we did wrong is not wait enough.
Here's our answer. All right, so I see a few more questions coming in. Edvinas is asking, having never used multi-threading, a few words on profiling, please.
Yeah, profiling is a separate topic. Actually, it is really hard. It's harder than it looks because in order to profile your application well, you have to know a lot about the environment it will run on. Because one thing is running something on an old dual-core processor. Another thing is running it on a modern high-end Ryzen, which has a lot of threads. And you should also keep in mind that you also have to think about what else is going to be running on that machine. So if you have a full control over the machine and you know that nothing else but operating system in your application is running, is one thing. If everyone's using the same server, like it's some kind of, I don't know, shared server or something, then it's different. You will have many cores, but some of them are going to be taken. If you want to be gaming on a PC, while something is calculating computing in parallel, you will have a few cores taken as well by your game. So you have to know a lot about the environment. And on profiling, it depends on what you want to measure. There is a classic Python timeit module where you can measure the full execution time. I'm not sure if Python has any tools, any good tools for calculating full execution time, the CPU time. Maybe this is better done by some Linux utilities where you can measure the full execution time, because full execution time will always be larger than just running everything on a single process. It's just that you spread it across several cores. So I'm not sure if I answered the question fully.
And I think we have another question is from Shimkus. Is it possible to use multi-process or multi-threads to load and parse Hue XLSX files?
Short answer is yes. Long answer is it's not that easy, but it's achievable. If you have a mix of input-output operation, and which is loading the file, and it's a single file, so you cannot apply something that we did here with images, where we had different images. It is a single Excel file. The load of the file is hard to parallelize. I don't think that Python can offer something like that. If you have enough RAM to load it fully into memory, then parsing it should be easier because you can split it into chunks and then parse those chunks separately.
I can chip in on this as well. I've actually did something similar. So in our XLS, we had a structure where we had one, let's say, common object, which is required for all the child objects. And I would take that and split the child objects by seeking in the file. I jump to a random, let's say, location if I want to split it into 4 pieces, and find from that location the first ending tag of the element that should be considered as one unit. Once I have all the units, I spread them across all the processes. Well, once I have basically the check marks from where it has to read to where, I can spread them across processes. They read only that chunk and parse it like that, using the common element if it has to kind of share some of the XML structure.
Right. So I do see another question. I guess we will have one more question, and because we are already over time, another thing is that feel free. I've talked to the speakers, and they are definitely agreed. If you want, you can find them on social media, on Facebook, on LinkedIn, and you can even dive deeper with them with the questions and suggestions they might present to you. But another message we received from Daniel, you can also look at Dask that sort of parallelizes pandas. Any comments on that?
I haven't really looked at Dask really much, so I would not have many comments on that, but yeah, it's common for something else. But yeah, parallelizing something with pandas or NumPy is a little bit different than just parallelizing pure Python code, because those are written in probably C and loaded as C library, so they achieve concurrency at sea level. So we are working above sea level in the mountains, and we just use whatever they give us. So if you're running pandas or NumPy, they have some kind of parallelization already. So they are probably utilizing more than one core already.
Yes, and be careful with distributed computing with software that spans across multiple instances, because sometimes just running on a single instance and using a cloud provider instance that has like 1 terabyte of RAM and 100 CPUs is much more efficient for smaller data sets. That data set, the smaller data set can be like 30 gigabytes or something. Then trying to split that out into instances, and that's especially true for something like Apache Spark, which has the PySpark basically wrapper around it. So.
Yeah, and I would also like to add, if you're going to have a lot of CPUs, like hundreds or thousands, there are libraries like MPI that specialize on sending messages across those nodes, across those processors, and they should be used instead of just pure Python multi-threading or multi-processing or whatever. You should then look at those libraries.
All right, so thank you guys so much for these great presentations. While I'm giving my, end speech, I just wanted to say also big thanks to everybody who joined today. If you think that there is a topic that you would like to hear about in the next meetup that we're planning to have, feel free to share your ideas. If you think that you want to participate as a speaker, also feel free to reach out to me. You can find me on, LinkedIn, Facebook. You can always, just text me, and we can arrange something. And I see a lot of thanks So, biggest thanks is, to speakers and to all the attendees. If there, aren't people who are joining and presenting, we couldn't do this. So, it's much, hugs to everybody, virtual hugs, not physical, because we can't do that right now. And yeah, so for the next meeting, we're thinking of having, a separate Discord channel that we think of running after the presentation, so you can, dive in more deeply into the, the topics and ask questions, discuss about what you want to know. And to close this off, again, thank you so much, and we will keep you posted with the upcoming meetings.
Okay, thanks again. And I guess it's goodbye.
Yes. Bye, everyone.